So our first speaker today is Kadie. Carl is the leader of the FastLMM open source genomics project, and he's going to talk about how to optimize Python for slowness. I think he's going to connect back Python to the foundations of theoretical computer science.
Thank you. So I am going to talk about something a little different. Everybody else will tell you how to make Python faster, and I'm going to tell you how to make it slower. At the end, we'll actually take a little bit of time to look at least one technique to make it faster. So it won't all be about slowness. A little bit about me. I am supporting a genomics open source project. Previous to that, I was a research programmer for most of my career at Microsoft and Microsoft Research. Sometimes something gets me on a tangent topic, and that was the case here. I got interested in some new Turing machine results that we'll talk about. And I wanted to understand it better, and Python's a great way to make things more understandable. So we'll learn about those results. We'll also learn some things about large numbers, including representing large numbers in Python. And like I said, at the end, we'll actually learn at least a little bit about getting some speed-ups. The way this is going to be organized is we're going to try to write short Python programs that run for a really long time. And we'll set that up as a kind of a series of challenges where each challenge will have some rules. So for the first challenge, we just want a Python program that runs as long as we can think of. Any suggestions on the kind of the obvious way to do that? Infinite loop. There we go. And in Python, there's nothing easier than writing an infinite loop. While true, do nothing. So let's evaluate this. This is nice and short. It uses almost no memory. Maybe the only downside to it is it doesn't halt. Not that that's necessarily bad, but what if we added the extra constraint that we want a program that runs a long time but also halts? So let's make that rule set 2. Whoops. Any guesses on how we might want to make something that runs a long time but does eventually halt? Yes? She says sleep big number. I'm not going to do it that way. I don't know why. Just a different way. A date. OK. All fine. What if we don't have any access except we can run the program? We can't access any outside library. Nested loop. So that's what we're going to do. We're going to do nested fixed range loops in Python that might look like something like this. For A, in the range 10 raised to the 100th power. For inside that, for B, in the same range. And just so we see some output of this, every 10 million steps, we'll print out where we are. And if we do that, we'll get 0, 0, 0, 10 million, 0 to 70 million. And then I got bored and hit Control-C. Let's analyze this. We have 2 nested loops. Each one's running 10 to the 100th power. So together, they're going to run 10 times 10 to the 100th power. That's 1 Google squared, 10 to the 200th power. The fastest computer we can imagine can maybe do 1 step every Planck unit, which is kind of the smallest possible unit of time. So if we're doing 10 to the 200 steps, and there's 10 to the 50th Planck units in a year, then this little program will take 10 to the 150 years before it finishes running. The universe is only going to last for 10 to the 100 years. So we've already got something that is going to run longer, half again longer than the length of the universe in just this much code. This uses about 144 bytes of memory, but a nice desktop computer has 64 gigabytes. So what if we just nest our loops to use all the memory in kind of a standard computer? Now, just with the same technique, we can run 10 raised to the 100 billionth time years of computation. So maybe we should be done, because if we've got something that halts, it's still super short, It's using just a fixed amount of memory, the memory that we have either in this little program or on our computer. But maybe just for fun, let's relax that constraint of bounded memory. What would happen if we aren't restricted just to kind of the practical memory we could get on a computer, that we're allowed to use an indefinite amount of memory? Yeah? We'll see some things that are recursive or close to being recursive. But I'm going to attack this next part with unbounded memory a little differently. We're going to start by using a Turing machine to represent what we can do with unbounded memory. So a Turing machine is an abstract model of computation. The kind of interesting feature related to unbounded memory is that it has what we think of as an unbounded tape that can go as far as we need in either direction. Each cell on the tape can hold only a 0 or a 1. It's going to start out all in zeros. The Turing machine works by reading the value at the current read head. You can see the little triangle on the picture. Then it'll write a 0 or a 1, and then it'll move either one spot to the left or one spot to the right. It's allowed to have, the Turing machine's allowed to have its own state. And this is a variable it can look at that can only have some fixed number of values. So in this first case, if we only have a 5-state Turing machine, they can only hold the character A, B, C, D, or E. We'll sometimes see an H that doesn't count against our, when we're counting states. It doesn't count as one of our 5 states. And now a Turing machine program, that means it's just a table. Given what state we're in, say state A, what the value we've just read from the tape, 0 or 1, we just look up this triple, and it tells us what to write, what direction to move, and what state to move into. So let's look at an example of that. We're always just going to decide to start in state A. We read the 0. We look at that table. It says 1RB. So we write a 1. We move to the right, and we change our state to state B. Now we're in state B. We look at the table. We're reading a 0. It says 1RC. So we write a 1. We move to the right, and we move to state C. So every step that we're executing, we can think of the Turing tape like at that step. We can at least imagine what the tape was like on the previous step and on however many subsequent steps. We might not really record all of this, but at least in our imagination, we can think of all the different generations of the Turing machine tape. We can make a picture out of this. We're going to leave the zeros as some background color, and we're going to color the ones with some foreground color. And then if we go a little farther and execute more steps, we'll get more of a picture. Just to make it fit my screen better, I'll make it a little bit wider. And on this particular program, that 5-step program, we can let it keep running and see what the pattern we get as the run keeps going. So now we're at 1,000 steps. The last row that was the Turing machine tape at 1,000 steps. 50,000, 100,000, 1,000,000, 5 million, 10 million, and it stops at around 47 million. What's up with that? So this 5-state Turing machine halts after exactly 47,176,870 steps. Furthermore, there is no 5-state Turing machine that runs any longer. And it's like, well, how could they know? Did they try them all? It was proven by an amateur research project called the Busy Beaver Challenge, bbchallenge.org. In 2023, it was a human-generated proof, but the proof was validated with a computer proof verification system, so we can trust it. We can, now that we have this Turing machine, we can get a Python program that has the same capabilities just by emulating a Turing machine in Python. And that's very straightforward. It's fast, it's simple, It's still using fixed memory, except we have to somehow represent the Turing machine tape. And the way we'll represent that tape is with two lists, one to represent the Turing machine tape going off in the positive direction and one going off in the negative direction. And when we do all that, we get something that halts, so that's nice. It's still a fairly short program. It's exploiting this unbounded memory, and it only runs 47 million steps, which isn't even as much as we got with two nested loops. So that didn't seem like it worked. Let's try one more thing. We'll just add one extra state to our Turing machine. So now instead of a 5-state Turing machine, we're going to have a 6-state Turing machine, this particular one, and let's let it run. 1,000, 100,000, 1,000,000. We've passed 47 million, 1 billion, 1 trillion, 10 trillion. Okay, did it stop at 10 trillion? No, it's still running. I just got tired. I just got tired of watching it run. So this program, if we could let it keep running indefinitely, would actually run for 10 raised to the 10 raised to the 10 stacked 15 high steps, and then it would still halt. So the way that's represented mathematically is 10 up arrow 15. The operation of up arrow is called titration. Just as a reminder for exponential notation, 10 to the first power is 10, 10 to the 10th power is 10 billion, 10 to the 10 to the 10 is 10 to the 10 billion, 10 up arrow 4 is already more atoms than there are in the universe, and 10 to the up arrow is 15. We could say that's a number that's so big that it's annoying to write in exponential notation. A person who works with the BB Challenge org proved in 2022 that this particular 6-state Turing machine does halt after that many steps. It's not known, and it may never be known, if this is the longest running 6-state Turing machine. But again, just like with the 5-state, we can easily interpret this in Python. And if we do that, we now get something that halts. The program is still relatively short. It exploits the unbounded memory we talked about. And now we've got something in Python that runs for 10 to the up arrow 15 times, which is way more than we got with the nested loops. But there's still a problem, or at least something not desirable, and that's that it's very hard to analyze this table and understand that it runs that long, or be confident that it does. So let's create rule set 5. Now we're going to try to make a plain, relatively understandable Python program that runs for 10 to the up arrow 15 steps, at least, but without using Turing machine emulation. We're going to try to write it in plain Python, and we're going to try to make what it does obvious instead of obscure. Our strategy will be to use something that you might be familiar with, and that's that we can define addition in terms of repeated increments, and we can define multiplication in terms of repeated addition, and we can define exponentiation in terms of repeated multiplication, and we can define titration in terms of repeated exponentiation. So what does that look like in Python? Let's start with increment. The first thing we're going to do is import, I'm going to call these fancy integers. So we're going to import gm pi2 from xm pi z. And the reason we're doing this is because normal Python ints, while they can represent arbitrarily large integers, every time you do something like add 2 of them or even increment 1, you get a new one. It does a full copy. So what we want is something that where we can have unbounded integers, but that we can update them in place without copying all this giant memory. So our Python definition for increment will be, we'll input one of these fancy integers. We'll check that it's the type that we expect it to be, and then we'll just add 1 to it. And we can run a little program. We can set b equal to, we can set b equal to the fancy 4. print its value, increment it, print its value again, and we'll see that 4 plus plus increment 4 is indeed equal to 5. So we need some restrictions here. So we're going to restrict that in our main program, the only thing we're allowed to do is initialize these fancy integers to 0. We're only allowed to do increment and decrement by 1, and we can compare with 0. So specifically, we're not allowed to copy these giant unbounded integers. We're not allowed to use any temporary values, and we're not allowed to do any other arithmetic operations. Then we'll check the type. So we've got increment. Let's see how we can build addition. Somebody mentioned recursion. We could be doing all this recursively. I actually got it all working recursively, but with recursion, I didn't have as much confidence that I wasn't accidentally making copies of the integers. So I tried to write, so in this case, everything is written right here. And in fact, even though I'm doing the same increment we just talked about on the previous slide, I'm embedding it in the addition instead of calling the increment function. I'm inlining, and that's just so we can see everything at every stage. So in add, we're going to have 2 inputs. One's going to be a plain Python integer, and the other will be one of our fancy integers. We'll check the 2 types, and then we'll just loop a times, and on each time we'll increment, and I think you'd believe that when we're done, that's a way to add some number to what we had. So here 2, we'll add a fancy 4. We print it before, and we print it after, and we'll see that 2 plus 4 equals 6, like we'd expect. And I also did an ID check to make sure that the fancy integer we have at the beginning is the same one we got at the end, that we didn't accidentally copy it. This is the most important one to understand. So how can we do multiply in terms of repeated addition? So again, we'll take a regular integer. We'll take one of these fancy integers. We'll check their types. We'll set something called the add accumulator to 0. And then we'll loop whatever our multiply accumulator number of times is. And for each one of those loops, we'll add a to our add accumulator. And hopefully, it's kind of clear that if we loop the multiply number times, and each time we add a, that at the end, the add accumulator will be the product. One thing's funny here is we can't use range on these fancy integers. We need to do something else. So in Python, it's very nice. It's very easy to write your own iterator function. So we just say if we want to loop whatever an accumulator is number of times, then all we have to do is check if it's greater than 0. And if it's not, let's see. If it is 0, we just end. And if it's greater than 0, we decrement it by 1. And then you just yield nothing. And that'll let us loop that number of times while still staying within the operations that we said we needed to. And we'll set, just as an example here, we'll have a equal to simple 2, b equal to a fancy 4, and we'll print c equal to the multiply of a and b. And if we actually do this, we get 2 times 4 equals 8. I'm going to skip exponentiation. It works the same way you'd expect. But let's look at this highest level one, the titration. So we start with simple a fancy tetrate accumulate. We check our types. In this case, we have to make sure that the a that we're operating on isn't 0, because 0 up arrow b isn't defined. We're going to define an exponentiate accumulator equal to fancy 0. And then we increment it by 1. And that's because we're going to be doing repeated multiplication. And if you do repeated multiplication starting with a 0, you're going to be unsatisfied with the result. What we would like to do now is take our exponentiate accumulator and loop a raised to the exponential accumulator number of times. But we're not allowed to do this because we're not allowed to do this fancy, we're not allowed to do an operation like exponentiate directly on a fancy integer. So instead, we'll just substitute in what we got from the previous slides. And you can see, since we're doing this over and over and over again, and each time our exponentiate accumulator is getting bigger and bigger, then these values will get bigger and bigger, and we'll get the final result. And we can test this on a very small example. 2 up arrow 3 is indeed 16, because it's 2 raised to the 2 raised to the 2, stacked 3 times. So let's look at what we have here compared to what we had when we were just doing the nested loops. With nested loops, we had 2 for loops. They were statically bound to some fixed value, and we could just look at it and see that it would go to 2 to the 10 to the 200 times. Now we've got 4 for loops, but the bounds for each one is changing. As they're looping, the amount of looping the next time through will be higher. We can call it with 10 and 15, and we can kind of be sure that the inner increment will be running at least 10 to the up arrow 15 steps. And this gives us what we wanted. Now we're halting. We still have a relatively short program. We're exploiting unbounded memory. We're getting this humongous number of steps like the Turing machine did. And at least compared to analyzing a Turing machine, we have something understandable. So if you want to run your Python program slow, we can summarize what we've seen with these recommendations. If you want them to run forever, use an endless loop. If you want it to be statically bound, or if you want to have finite memory, then use the endless loop for running forever, nested loops to run with a long time but have bounded memory. You can use emulated Turing machines to get maybe the shortest program possible, but they're hard to analyze. And we can use this dynamically bound loops that we saw last to get us the same kind of super long runs, but it's much easier to analyze. With that, let me talk about how to make some of this stuff run faster. And I'll just only mention one technique. Suppose we just want to emulate a Turing machine with the Busy Beaver 5 champion, the one that ran 47 million steps. And we want to do this in pure Python. So the core code is here. It's straightforward. We loop as long as we haven't hit the halt state. We read the tape symbol. We go look up in our program what the next action is. Then we pull apart that action and set the new tape, move left or right, and set the next action and keep our count step. And if we do that and run this on the Busy Beaver 5 emulation, it takes about 26 seconds, which I don't know. I mean, that seems OK, 47 million steps in 26 seconds. But can we do better? The speed up recommendation I'm going to make to you is have Python call a Rust language extension. And I've got another article about that, 9 rules for writing Python extensions in Rust on Medium. The Rust code doesn't look that different than the Python code. Again, this is the center of it. There's some decorations at the top to do the interface with Python that we loop however many times, and then we just ask the machine to give us its next step. If it has a next, we remember whether it has a next step or not. If we increment our count by 1, and if it doesn't have a next step, we break out of our loop. So the Rust code isn't particularly any more complicated than the Python code. And the nice part is when we run this, it'll run in 0.211 seconds. So we've just got 124 times speed up. The downside to this, we've now introduced a second language. The second language is fully, that's a minus, of course. The second language is fully compiled, but which is why it's fast. It's memory safe, which is why people like it. It's relatively straightforward to connect. It is straightforward to connect Rust with Python because there's a nice library called PyO3. The other downside is even though I'm a fan of both languages, I'm 10 times more productive writing things in Python than I am in Rust. So In this case, it's probably worth doing this because I'm getting 100 times speed up, but my actual coding time is going to take longer because I'm using a language that's not as productive to write in. We can do better. So what if instead of having Python call Rust, we have Python go right into assembly language? I'm going to do that via Rust because that's the way I know how to do it. The code looks kind of nice at first. This is Rust code using what's called a macro, but this macro expands at compile time and turns into one block of assembly language code like this for each state in the Turing machine. But it works. If we run this compiled assembly language, we can run this Turing machine in 0.34 seconds. So that's a 750 times speed up compared to the Python. I actually don't know assembly language. I was using agents to help me write it and annotate it, but I think I got it working well. The intuition about why the assembly language runs faster is because, like most modern languages, Rust doesn't allow you to use goto. And when you're writing a Turing machine, goto is kind of what you'd like to do. And being able to do it directly in assembly language makes things faster. So now we've introduced a third language. So right now, that's even worse. But this is fully optimized, I believe. A downside is it only runs on one kind of computer, an x64. And it's no longer memory safe, because in assembly language, you can do anything you want. So when I actually run this thing, like to 10 trillion, only 6 hours of that was emulating the Turing machine. 45 hours of that run was visualizing the Turing machine and averaging all the pixel values to make pretty pictures. So by making 6 hours 5 times faster from Rust to assembly language, that only turns my runtime from, well, if I did it in pure Python, doing the full visualization would take 2 years. But with the Rust extension for the visualization, it was taking just over 2 days. And if I add assembly language, it's still taking just over 2 days. So for these runs, I didn't actually use the Turing machine emulation, because for these purposes, the Rust was fast enough. For the Rust, I also did some speed ups, and I've got another talk, how to optimize your Rust program for slowness, that talks about some of the SIMD and multi-threading optimizations I did in the Rust to make the visualization run faster. So just for this conference, I wanted to set a new world record for doing the visualization. The old record was running that BB5 contender for 10 trillion and 1 steps. So a week ago, Wednesday, I started a run with Python extension making the run, and I told it to go to 10,002, because I didn't see any reason not to do it just a little bit. And it finished last Monday. There were a few hiccups and 1 restart. Oh, sound. So here's the world record, as far as I know. You'll see, there's a 2 there. There was 0, 0 before. So thank you for joining me on this journey through Turing machine results. Let me give you some links and resources. There's a GitHub project that has Python notebooks that you can generate your own visualizations and anything you've seen here. The articles I mentioned is running Python slow, which is exactly what I'm talking about, doing Rust extensions in Python, and running Rust slow, which has some additional optimizations. There's 2 versions of the visualizer available on the web. They use Rust and JavaScript. One of them, this takes you straight to, and you can even run visualizations on your phone. I'm also happy that the bbchallenge.org organization is using my visualizer as one of their 3 visualizers. So if you go to the site and select the Blaze visualizer, you'll see that. And also, I have a very tiny YouTube channel where I've put some of these visualizations, along with a few other unrelated things. So thank you, and I'm happy to answer any questions.
Thank you very much. So we've got roughly 10 minutes for questions now. So we went from the lowest level programming language to the highest.
Thank you for this talk. This was really cool, and also your visualizations were like really awesome. So I know a bit about Googleology kind of like as a hobby side, and I thought it was really cool that you're bringing it kind of like to practical applications as well. So I think what's interesting is, well, what I want to ask is, how did you start to conceptualize this idea of slowness and how it relates to like fastness and like going the other way? Like, how did that start?
Let me give two motivations. My first motivation was these results on the Turing machine, the proofs that these are the longest or how long they run, have only come out in the last year or two. And when I went to the website, because I was interested in it, all the visualizations were black and white, and I thought they were ugly. But when I went to Wikipedia, the visualizations were yellow or orange, whatever color you'd call that, on white, and I thought they were very pretty. So part of my motivation was I just wanted to make the visualizations prettier, because I could see that they could be pretty. The reason I got interested in the slow and the long is because I believe that those results on the Turing machines really do run that long, but I couldn't see it, right? That proof, or even understanding that proof, even reading a few lines of the proof that that Turing machine runs for 10 to the up arrow 15 times was like something I couldn't comprehend. But I knew that if I could turn it into a Python program that fits on one page, that in a sense, I would understand it. I think I'm enough of a computer person that anything I can write a computer program for, I feel that I understand it, even if I couldn't do it on my own. So by doing this, I now feel like I understand what these large numbers are.
Any further questions?
I can give you just one thing that was a speed up in the Rust. So I don't know how accessible Python makes SIMD optimizations. So SIMD is this ability that all our computers have had for the last 20 years to do multiple simple operations, use the arithmetic operations and some logic operations on up to like 64 numbers, all in one step and all on one processor. It doesn't even count as multiprocessing. So for doing the visualization, to make it look nice, I needed to not just pick a pixel. When I'm compressing the picture down to something that would fit on a screen, I've got like 10 trillion rows and maybe a few million columns, and I need to compress that down to a single pixel, which should be the average of everything in all those Turing tapes. So I'm often taking a bunch of 0, 1 values and needing to turn them into some range of values between 0 and 256. And SIMD operations made that like 6 times faster. And it's free. Turing machines are notoriously hard to multiprocess because they're so sequential. But in this case, the SIMD operations were running on one processor. Didn't cost me anything. It's just processing power that we all have in our computers, but that a lot of our programs aren't necessarily taking advantage of. So that was fun to exploit.
I have a question. What was the largest amount of memory that you used for storing Turing tapes?
That's a good question. Actually not that much. Because I knew it would be a problem from the very beginning. I knew on the visualizations that if I did anything close to holding all those Turing machines, I couldn't generate all 10 trillion by, say, 1 million at the beginning and then reduce it, compress it into pixels. So it tries to be very smart at always keeping running totals. So until it gets the size of the final image, it does keep all the Turing things. And then as you get more rows, it keeps going. But as soon as it gets past twice of what you want, it compresses the picture in half. It averages all 2 rows into 1. And now the picture is only twice as big. And now when it gets a new row of the Turing machine, it holds it. But as soon as it gets a second one, it averages those together, and those become 1 more row. So because it's always compressing things on the fly, the memory is quite small. It's never much bigger than the size of the final image.
Thanks. So the images are not infinitely zoomable.
They are not infinitely zoomable. It would be very fun to make a visualizer that would let you zoom in, and maybe it would certainly be aesthetically pleasing, but it would completely go against every optimization I made from the beginning. So it'd be starting over.
Thank you.
Yeah.
Well, thank Carl again.
Thank you.